Okay. So, yeah, we're good to go. What's this, David?
That's a Dratini.
That's a what?
A Dratini. It's a Pokemon.
So what we'll do, last lecture of the semester, we're going to finish up Maximal Schwarzschild geometry. What we have done was we had, just a quick recall, we had defined t-bar previously. Natural log of r over r star minus 1 and ct tilde ct minus r minus natural log of r over r star. And we said, what will the metric look like if we use ct bar, ct tilde, theta, and phi? And we wrote the form of a metric. But what we realized, and for example, so far what we have done is when r is greater than r star. There's no real difference. You just have to just keep track of sign. So when r is greater than r star, this absolute value, well, I can give you this, is just that. Okay, that when we study the interior geometry, the only thing is that sign changes. These are just almost algebraic. And when we wrote the metric, if you look at the Schwarzschild metric, there's this 1 minus r star over r in the metric. And this is a problem, especially if you have in the denominator. So our goal was to try to get rid of this factor. And we were able to do it. And to do this, and again, when you look at the math, it is kind of puzzling as to why we proceeded in this way. But now that we know the story, you can backtrack and see why that would have worked. And I bet, I think Finkelstein may have tried several combinations and landed upon this one that worked. So we had to define a new set of coordinate system, e to the c t bar over 2r star, and q was, I think, minus e to the minus c tilde over 2r star. And with this definition, we changed our variables, the coordinates, to p, q, theta, and phi. And this is where we ended up, as in doing so, we ended up with the expression minus 4r star cubed over r e to the r over r star dp dq plus r squared d theta squared plus sine squared theta d phi squared. Again, to be very clear, this calculation was done in the exterior geometry. Okay? And you can see this term does not appear. So and this is no longer important to us. Anyone who works with even Minkowski geometry in various coordinate systems immediately knows what to do with this. So we'll go to a final coordinate system. And in the final coordinate system, we will bring back a new time. And it's defined C uppercase T to be P plus Q over 2. And for lack of a better term, an uppercase X to be P minus Q over 2. And then dP dQ is easily calculated. What is it? C times dt, 2C times dt equals dp plus dq, and 2x is equal to dp minus dq. From here, you can solve for dp and dq in terms of dx and dt. I would like you to do that and put it back in. It is so simple that I'll write this. The factor remains the same because we're not really messing around with the factor at all. R star cubed. See, there's a minus over here, but I believe that goes away. E to the R over R star. You get a minus, very nice. Look at this. For a Schwarzschild solution, but do not mistake this for X in the traditional sense, because what follows is a this is the final form of the metric we need. And the coordinate system here is, well, CT, X, theta, the Schwarzschild metric for outside the event horizon in this coordinate system, at least the invariant interval looks like so. Now we can start drawing diagrams. That's literally what we'll end up drawing. And gosh, we had so many coordinate transformations to get here. But I remember T and R and theta feed from the original metric, right? So what we'll do is we'll get rid of all the intermediate steps and find a relationship between the various coordinate systems. So I may need this. Well, let me hang on to this for a second. So my goal would be to find the transformation between and you, at the end there will be a story. Okay? Now it's just one unmotivated transformation after the other. But this is very important. This is P minus, what is it? CT is P, I don't have P minus. No, I need to change into this, but Q has a negative sign in there. 1/2, I'm going to put down what P and Q are. This is E to the CT bar over 2R star minus E to the minus C tilde bar over 2R star. And then we're going to expand this out with these guys. Remember, outside the black hole, I can use simply this expression. So I'm going to replace with this. I've been careful in my algebra, so please verify at your own time that this is correct. If you find an error in the notes, please let me know. I'll pause and explain what we have done, although it should be fairly clear. See, when I do this, I get E to the CT. And this R becomes that. Because there's 2R star, I get the 2R star. And oh, wait a minute. Was there an R star here, guys?
Yes,
There was?
I believe so.
Good, good. So we cut that R star, because I don't see the R star here. Look, otherwise there would be like 2R star here. I don't have it. That's because it goes away from there. But I know what's e to the natural log. What is e to the natural log? Whatever the argument is. So, I'm going to write it here in the box. Ct is equal to, whatever the argument is, I take the 1/2 over here and square root it. R over R star minus 1. This guy remains the same, e to the r over 2 r star. This, you can easily verify, this is sinh of Ct over 2r star. This is precisely sinh. So in exactly the same way, I'll get e to the r over 2 r star cosh Ct over 2 r star. So let me box this guy for you, because we'll use this. So this is a complete set of, nothing is done to theta and phi. Theta and phi are just along for the ride. So if you take the original Schwarzschild coordinates and the original Schwarzschild metric and make this transformation, this is the metric you end up. Now, why is this a nice looking metric? But there's so many good features about it. Well, this part is just a sphere, because its Schwarzschild is spherically symmetric. This is almost like Minkowski, with just a positive function outside. And r equals r star is not an issue, but what is an issue? R equals 0. I've mentioned this before. R equals 0 problem. It's not going to go away. So I'm going to start. I want to draw a diagram. But any questions? Can I draw a picture where we get a handle of what's going on? Okay, that's my goal. If I need to, I'll rewrite this metric. To draw a diagram, just in the axes and whatnot, because this is a nice coordinate system. There are no infinities at the event horizon. So if we can draw something nice, it will be very helpful. I want you to notice a few things, but let me graph a few of these functions. This is the graph of cosh x. This infinity is the graph of sinh x. And this is the graph. I write that because there's sinh and cosh over here. It'll be easier for me to have the conversation with this diagram to consult. So as I try to draw this, I immediately say that x should be greater than or equal to 0. Actually, I say greater than or equal to 0. Correct, because this can go to 0. Yeah. X is never negative. This is never negative. This is never negative. And cosh is never negative. Correct? So let me try to draw a Cartesian-like axis. I want to draw a Cartesian-like axis because what I just erased, it's minus dct squared plus dx squared. It's very much like Minkowski. So with that in mind, I need, well, I don't need this. This is my x, this is my ct. First thing, this graph, which is outside the black hole, is in this region. Correct? Because x is greater than 0. Okay, can't do much with that, but d ct over x is equal to tan of ct over 2 r star. Now ct can go from, or rather t can go from, little t can go from minus infinity to infinity. But look at tan. It only goes from, so that means ct over x, I'm going to write the next line over here, minus 1. This is the line ct equals x, which means ct over x equals 1. And this is the line ct equals minus x. So whatever is outside the black hole is where? In this region. We good? Point number C. I think sin squared minus cos squared must be 1 or something like that. And I think it is, or minus 1, because I see this over here. If r is a constant, this is a constant. Correct? What will t squared minus x squared equals constant? What is that the graph of? Lines of constant are hyperbolas. You can divide by this and you get, what is the equation of a hyperbola usually? Right? So whatever that constant is, you can divide by, or you can maybe extends to that. In this case, that's what it would be. So that means this is r equals constant. And you can plot for different values as r increases, the hyperbolas go out further than. I'm assuming at this point you have committed the graphs of trigonometric, hyperbolic trig functions to memory, because I need to move on to describe something else. Okay, so I'm glad I kept this. As r goes to r star, we're tempted to say Oh, I want to mention something else first. Might be helpful. Where is it in my notes? Yeah, I'll get there shortly. As r approaches r star, what are you tempted to say? 0. That's not true. It would be 0 except when t goes to plus or minus infinity. Because 0 times infinity is not well defined. Yeah? But we can nonetheless see from here c squared t squared minus x squared equals 0, or ct equals plus or minus x. So that's odd, but it's not. So this line is really the horizon. And that's good, because we know the horizon has a null geodesic. And null geodesic we typically draw at 45 degrees. All kind of worked out. It's a true horizon, but there's one more feature I want to mention, which is, where am I coming to? Yep, as CT, I don't think I have that written there. Yeah, as t goes to infinity, CT over x goes to 1. So that means this is also the line t equals infinity and t equals minus infinity. And I guess I should have mentioned here, this is not a good sentence. My heart was in the right place. I said lines of constant r. What I meant by that is curves. Hyperbola is not a line. It's a curve. But from here, I can indeed write lines of constant, well, curves of constant t are lines. Curves of constant t are lines. Because if this is a constant, it will be ct equals a constant times x. So, for example, this would be the line t equals constant. As a matter of fact, when little t equals 0, so this line right here is t equals 0. So t equals 0 goes all the way to infinity, and this is from minus infinity. Obviously, in this diagram, I've shown you 1/4. There's sort of a pi wedge over here. You can imagine a pi wedge over here, here, and here. So we need to complete this diagram. Turns out, this is really all we need. In this one, this is outside the black hole. Huh? All of this has been done only outside the black hole. Because we, right from the beginning, in the coordinate transformation, we assumed that r is greater than r star. So I should make this clear. This is outside the black hole. Okay? Inside the black hole, what's the only difference? The absolute value will have a negative sign. So when r less than r star, r over r star minus 1 is equal to 1 minus r over r star. So all the expressions change slightly. All my transformation looks similar, but to end up with a metric that looks exactly the same way, now we have to define Ct to be p minus q over 2 and x to be p plus q over 2. If we did that, we would get, I forget what it is, but I know what this looks like. There's a function over here, and I'll write this for completeness, don't worry. Let me copy that down. I would get the exact same expression, which is where? 4r star cubed over r e to the r star. So this is different, right? What's the difference? For inside the black hole, it was p plus q. Yeah, we just swapped x and t.
Negative c squared.
Negative c squared. Because it's the same expression, I can draw the same diagram. I have given step-by-step instruction on what will happen. This part would be t equals negative infinity. Once again, this will be t equals constant. And then I would get r equals constant, because nothing is changing. R equals constant. But there is one interesting feature. This is inside the black hole. What's the smallest value that r can have? Which cannot be included in our space-time. R equals 0. So there will be a hyperbola, and let me do it this way. This is r equals 0 singularity. So this is the black hole region. And my notes will have all the details of how this came about. Now so we have this black hole and the entire outside and inside just nicely drawn. So imagine how people in this universe could live. 45-degree lines are light-like. So you could choose to do I don't know. Today's one day I need more different color. You could choose to do this. Oh, maybe not 45 degrees. And and you could dash almost reaching the speed of light and just, live forever. Or if you made the wrong turn, now if I draw a 45-degree line, You can just fall in and die quickly, or you can wait a little longer. But you will hit the singularity. So this is the black hole region. This is the outside universe. Okay? Thankfully, this has two more wedges. That will fit just beautifully with this picture of a white hole. And I'll write down the transformations. So this is also, it should be a hyperbola like that, but r equals 0, and this is the white hole. Because, again, you have light cones that are 45-degree angles. You can, if something is in here, you can, it comes out this way, or it goes out this way. But this universe is not connected to that universe. So in some sense, this is the black hole outside and black hole region, white hole outside and white hole region. Okay, let me give you the coordinate transformation. It is very simple, almost rudimentary, but I just want to mention it. Interior geometry. Yeah. Transformation of the white hole geometry. So when r is less than r star, I can skip all the t bar, p, and all of that. Just go from ct and x to t bar and t tilde, and this is the transformation. It's really the negative of the previous one, but you can see it's 1 minus e to the r over 2r star cosh ct over 2r star, and x is equal to minus 1 minus r over r star over 2r star sinh. And then when r greater than r star, it's just that sinh and cosh gets replaced. Ct r star e to the r over 2r star sinh ct over 2r star. This is all in your notes. Minus 1 minus r star e to the r over 2r star. If this is sinh, the other is cosh. And if you use these two charts and look at, again, cosh is always positive. And you will see that just as we did the analysis here, it fills out this region. It's mathematically beautiful in the sense, if you are a beam of light here, you either escape and live forever, or a person you live and escape forever, or you fall into the singularity. You could have lived if you were an immortal being, you could be from this universe, just being here forever. Or you could have been kicked out of the white hole. But if you were kicked out of the white hole, you were not an immortal being. You were just magically created somewhere over here. But since r equals 0 here, all our math fails, so we cannot do analysis. I must say, few concluding remarks for this semester. A, while this exists, we don't know if this exists. We haven't observed a white hole region. If we didn't have this, we're happy to live with that. Okay, it is curious that these dualities exist so simply in Einstein's equations, but we haven't observed one versus the other. These are not issues that are settled. The other thing is, just because you have r equals 0 being a problem, it could be a failure of the Einstein equation itself. It may not be that the universe has singular regions there. It could be that someday people could come up with a quantum theory of gravitation, perhaps. It is speculation, to remove this singularity. Quantum mechanics has a way of removing singularities, removing classical difficulties. We say that because we have seen that in the past. So if you look at a hydrogen atom, if you just do classical electrodynamics, if you have a charge that's rotating, it's going to radiate. As it radiates, it loses energy, and it'll collapse. If it loses energy, the orbit collapses. But we see a stable hydrogen atom. And so quantum mechanics comes and says, no, there are beautiful eigenstates. And electrons, if they have access only to these many eigenstates, when you go to the lowest level energy shell, it cannot drop any further. All of a sudden, atoms can exist. The same thing could be true over here. Gravity could have a granular structure where this infinity breaks down. Or it could be a problem with the universe itself. This is literally a tear in space and time. And the other question, I sort of liken this to, why aren't we seeing a white hole? I don't know, I'm not an expert in observational physics, but in some sense we know, in cosmology there's an issue that particles and antiparticles are really one and the same object. They're just duality. And yet we see an abundance of particles versus antiparticles, at least in our part of the universe. But there the story is slightly different. In particular, we have observed antiparticles. We just haven't seen a white hole. If from a classical GR point of view, a white hole would be terribly bad, because for no reason it could emit data. Because we don't know what happens at the singularity. Something could be feeding it in. Right? There could be something over here. Somebody could come and drop a chocolate bar, and all of a sudden in the night sky, you see a chocolate bar. It hasn't happened. Yeah? So I think this is a good place to stop. You have your final exam already, so very quickly, next semester, the first chapter would be tensor calculus, just cleaning it up. You already know it, because we've done all the calculations. There's nothing much that is new except recognizing some facts. After tensor calculus, I can define curvature and the Einstein equation. We never wrote the Einstein equation, we just started with a metric and saying that, well, this is a solution, let's analyze that. And once we get a solution, we have some more time, we'll talk about the universe rather than a black hole. We'll talk about the space-time of cosmology, not what the universe is made up of. That would be a course in physical cosmology, but we will talk about the shape of the universe. There too, the end lesson will be exactly the same. Just like you have a singularity here, we'll have a singularity there. And that singularity is referred to as a Big Bang. The question then remains, is that a true singularity? Is that where the universe emerged from? Or will quantum gravity rescue it, and could we get to peak beyond the Big Bang? Whatever it is, it would have been even if quantum gravity would allow us to look beyond the Big Bang, something very drastic happened at the Big Bang. Yeah? So we'll get very close to it and describe the shape of the universe. That would be the topic of the next semester, which is part of the introductory sequence of general relativity. I think after the next semester, if you guys are so inclined, you will have access to more and more advanced books